just coin out the phrase black just to show that it is emissivity is actually 0.1. So the emissivity of the parameter which defines how black the body is what is called emissivity. Obviously, it will be a function of both wavelength and temperature. So the actual emissive power of a black body at a given temperature and compared to a black body, that is what is called the emissivity. Emissivity, of course, is designated as a complete like epsilon. Which English letters are మనకి కావాల్సిన నోటేషన్లో 50-60 కావాలి. సో మిగిలిన భాషల నుంచి ఫాలో చేసుకుంటాం వాళ్ళు. ది బ్రిటిష్ ఆర్ యూరోపియన్స్ బికాస్ Greece is much closer to them, they borrowed all the letters from Greek because they didn't know any other language. Had they known Telugu or other thing, they would have used this rotational period. But fortunately they didn't. Okay, now this we must expect that the epsilon also will be lambda on T. So this is what is called the spectral average in the hemispherical spectral average. Okay, wavelength to emissivity ఉంటే that doesn't make sense. I want to know what is average emissivity. Then what to do is just integrate it between the limits, integral 0 to infinity, d lambda, this one, this one. Obviously, you know that between 0 to infinity, d lambda is nothing but sigma t power 4 that we know already the plan. So we can calculate what emissivity is. Okay. Now, we have a black body, we don't have a white body because none of the Indians are really white in color, so we don't need them. So there is what is called a grey body. What is a grey body? Black body, grey body. What is a grey body? Of course, I have spelled grey with a GRA, but even if you spell with GRE, the thing is both spellings are acceptable. GREY also is a grey, GRAY also is a grey. A grey body is one which has emissivity is a function of lambda and T. And grey body is one which is independent of lambda. It's only a function of temperature, it is independent. So the difference between black body and grey body is black body, the emissivity is a function of wavelength and temperature. A grey body is something which has got emissivity, which is a function of only temperature, not wavelength. That's what that's the difference. Also later on we will see that absorptivity is also independent of angle of incidence because sometimes most of we will see what a reflect specular and diffuse reflection in a moment. It is independent of the direction in which the radiation comes in. That is what is actually another property of the grey body. Okay, now we will work out an example, and through the example we'll see what the values are like. Now everything what I told you may look like a magic. So this is actually a spectral distribution of at 1600 Kelvin. A diffuse surface has the following spectral emissivity at 0 to 2 microns. It has got emissivity of 0.4. 2 to 5 microns, that's emissivity of 0.8. From 0.8, emissivity equals 0. What I want is the average spectral average emissivity of power. How do I evaluate that one? So shall we apply the knowledge that we acquired in the previous slides? So what do we do? In this, what we want is average emissivity nothing but 0 to infinity, E lambda, E d lambda by E d. That's what we require. Now this is nothing but if it is split this one is between 0 and 2 and 2 to 8 and 8 to infinity is actually 0, so we don't have to worry about the integration part. So you can integrate just that. So because emissivity is constant, we have taken out if you can't see, come to the front. Are you able to see? Okay? Because if you didn't look at it, maybe you factor I got to check. I can't make it bigger because the screen is small. Okay. Epsilon 1 I can take the here is 0.2, here dB lambda. So then again from 2 to 5 I got to find out. And then you can say I don't have to worry because it's 0, so I don't have to integrate. So how do I do that one? So what I require is, then look, if the lambda t, lambda is how much is 2? What is lambda t? Because it's temperature of 1600. How much is lambda t at 2? Lambda times t, how much is it?
3200.
Calculate 1600 times
1600 into 2, 3200.
How much is it? Come on guys, you don't answer that expectation. I said you cannot come in. 600 అయితే what is this fraction? ఎక్కడ వస్తుంది మనకు? $3,300 లో ఎంతుంది వాల్యూ ఎంతుంది? 3,300 what is the value? So what it means is that 0.318 or 31.8% of the total radiation is between 0 and 0 and 2. Okay, note down that number. 0.312. That 0.312 is nothing but integral 0 to 2 microns e lambda t lambda divided by integral 0 to infinity e t lambda. Now this you said is equal to 0.318. Okay, round it to 318. Is that correct? Then we say 3,200 is 318. Get this one. This is not 318. Okay, okay. Happy? How to read that 318? Also, you can do it from the curve also. Okay. Lambda t 3,200 is equal to figure. If you take a scale and then plot it and then again, that just becomes a error. You will get that, but again, it won't be that accurate. That's why we use the chart for getting the exact number. Okay, 318. Has everyone got the number? 318. Okay, next we are going to find out. Next integral we require is between 2 microns to 8 microns, which is 208. How much is that? 2.5 microns, sorry. 2 to 5 microns. So how much is the, that is the
Notes will write there. That's sound like that.
That is not sorry, I think it is not E lambda by integral 0 to infinity. So this is nothing but if you have got two limits, what we do? We just separate them. That is equal to integral 0 to 5 E lambda d lambda minus integral 0 to 2 e lambda d lambda divided by integral 0 to infinity e d lambda. So this is 5 microns. So lambda is 5 microns. Temperature is 1600. So lambda t ఎంత వస్తున్నప్పుడు lambda times t, how much is that? I think I will concentrate on the guys in the back. How much is lambda times t? Lambda is equal to 5. Calculate rather than the 600 times 5. Please calculate, my friend. Take out my last take out the calculate. So lambda t is equal to 8,000. So lambda t 8,000 అంటే మనకి అంత ఫ్రాక్షన్ ఎంత వస్తుంది చూడాలి. So what we have to do? Go back to this chart. So 8,000 ఉంటాయి ఇక్కడ. ఎంత ఉంది? 8,000. 0.856 making a point. So d value is 0.856. It is not the 0 to the that how much is 0.318? Note down that number. 0.318. Correct? 0.318. How much is that? Use your calculator. That's the reason I wanted you guys to fill out your calculator. Please do the calculation. Unless you do the calculation. So now we will substitute that one into the equation and then see how much is that. 5.8 plus 8. Correct on that? So what I have got is right. Okay, now how do you calculate? Now F1 is at 0.4 because at up to 0 to 2 microns, it is 0.4 times 0.08. 0.8 this is 5 microns and 2 microns. So if you subtract this, that is, if you add this number is nothing but 5.8. So you go to the calculation, let me know whether that number is correct. Please do calculate. I will not proceed further unless every one of you have done calculation. You have to show me your book saying that you have done the calculation. Okay? Even if one person hasn't done, I won't proceed further. Because I want every one of you to understand this one. ఇది అవసరం లేదు ఇది కట్టవు కదా ఇంతకుముందు ఇది క్యాలిక్యులేటెడ్ ఆల్రెడీ 0.31 8.56 all these things you have got. You don't copy it from there. I want you people to do the calculation. మీరు లెక్క చేయాలి. I will give you an example. Do you know when you see the IPL and all these things where players play for 20 minutes, do you know how much of effort they put in for your 20 minutes of game? Every player puts hard work of 40 hours for your 20 minutes of game. Remember that. Similarly, when you see the football, when you see for 80 or 90 minutes of game, the players practice for about 8 to 9 hours for playing that game. And we are not, myself or Professor Anantapur, we are not asking you to do those 8 hours of work. Every 1 hour of class work, you just put in 1 hour of work is more than sufficient. And when you are doing that, please do the calculation. Otherwise, everything will look like a magic. Don't do that, man. You have the numbers. You calculate from there. Let's have it. You find even 8 together. You find a mind if you calculate. The board is not. You guys have to do the calculation yourself. There's nothing on the board. Okay? So whosoever has got the answer, then please show me your notebooks. Notebooks up. I want to see every notebook up and I'm going to check it. Let's go to the notebooks. Up.
రావడం లేదా సార్ ఒకసారి ఎక్స్ప్లెయిన్ చేయమంటారా అర్థం కదా సార్ ఏం చేస్తారా మొత్తం రాకుంటే సార్ అడగండి అమ్మా, సార్ చెప్తాను. చేయగలుగుతున్నారా? ఏం చూస్తున్నారా?
That is the spectral average emissivity for the whole thing. Integrate the whole thing. That's what So what is the total emissive power? Black body అయితే sigma times T power 4. Black body కాకపోతే you multiply the emissivity. So calculate that. Emissivity is nothing but epsilon. This is spectral average emissivity multiplied by sigma times T power 4. Calculate that. Let's go see it. Slow.
Sir,
You are going too slow. So చేయక బదులు అర్థం కాదు సార్.
వెరీ ఫాస్ట్ పోతే తట్టుకోలేరు సార్. దిస్ ఈజ్ ఓకే సార్, నాట్ స్లో సార్, ఇట్స్ ఓకే.
Okay, 0.538 water number times sigma 5678 that to 5.620 minus 8 multiply by temperature anta 600 power 4 like that.
చేస్తున్నావా బుద్ధి నాటకాలు ఆయన మీకోసం వచ్చాడంతా ఫ్యామిలీ వదిలిపెట్టి ఆస్ట్రేలియా వెళ్ళి.
Show me your group. I know that you are direct. Otherwise, you don't show your group. I wanted your book, madam, not your hand. Good, thank you. Done. Chela, show me your book. Show me your book. No, you sit down and show me your book. You said, you want direct? Show me the book. That's what I wanted. Show me your book that you are direct. Believe you. Only I don't know all the cases. We don't say that. Take your time. How much is that? Is that correct? What you saying? Huh? Yeah. Okay. Let's check what the number is here. But what we have done is we have multiplied into kilowatts instead of watts. So you might have got 207, then 3 more digits are there. So you know what you have done is calculation is correct. Okay? Is everyone happy with it? Okay, right. Now what we are going to see is vector emissivity and the variance. So we got to find out where the lambda max is, where at this temperature, where the lambda max is. What I mean is this is that is the emissivity. We want lambda, this you want ET, so we got this one as 600 Kelvin. So at this is what is called lambda max. So what is the lambda max at this temperature? How do you calculate that? How do you calculate lambda max at that particular temperature? What is the wavelength at which the maximum emissive power is? How do you calculate that? So we use the phase displacement law because lambda max times T is a constant. So lambda max will be simply equal to 2898, which is actually the phase displacement, the constant where 600. So you get that number. You see whether you get that 1.81. That is 1.81 micrometers. That's where the maximum emissive power will be there at this temperature. But this has got nothing to do with black body. Remember, phase displacement law is applicable for a black body. Okay, for a black, if it is not a black body, it won't occur at the maximum. It will just shift. Only thing is it will be proportionately less because emissivity is also a function of wavelength. So it may shift either way. So the lambda max, if it is a black body, it will occur over here. But this is what we have got now. It is not a black body because emissivity keeps on changing at various temperatures. It may not occur at the same point. So that we will not do that because that's asking for too much at this stage. So I will not do it now. Maybe at the later stage we will do it. Okay, is it clear? Of course, if you want to make a spectral emissive power, how much is it? Then actually you have to substitute into Planck's law and then where the lambda max and then you can calculate that. That I will allow you to do because that will take a longer time than what we can do in the class. So take that one as a homework, exercise, do it. Tomorrow class I want you to give me that number. Is it okay? Is all clear? Any questions, guys and girls? Is all clear? Okay, now we will go to the next one. Now, let me recapitulate what we have done so far. Emissive power is always defined by something which is a body which is actually giving out radiation. Okay, something is something like a donor. Like the Maharaj Poshakal antam kada, the emissive power is Maharaj Poshakal sambandhinchindi. Dhoni, people who receive, for them, the wording is different. We call it irradiation. I am entistunnaru. Then what is what irradiation? This is the emissive. If it is a black body, it will be just E lambda. If it is emissive power, if it is not a black body, then you have to multiply with emissive. That's what. I am just recapitulating. Irradiation corresponds to an object which is received. So, మన కాలేజ్లో ఇప్పుడు అంతా మీరు స్కాలర్షిప్ తీసుకుంటే కాలేజ్ ఇస్ దాత మనం emissive power అటు నుంచి వస్తుంది. మనము వీఆర్ రిసీవింగ్ ది స్కాలర్షిప్. సో వీఆర్ యాక్చువల్లీ దట్ స్కాలర్షిప్ ఈజ్ యాక్చువల్లీ సంథింగ్ లైక్ ఇర్రేడియేషన్ ఫర్ అస్. ఓకే. సో an object which receives the irradiation that we call it G lambda. So అది E, ఇది G. ఆ తర్వాత ఈ వచ్చిన రేడియేషన్ ఏమవుతుంది? పార్ట్ ఆఫ్ ఇట్ విల్ కెన్ బి రిఫ్లెక్టెడ్, పార్ట్ ఆఫ్ ఇట్ కెన్ బి ట్రాన్స్మిటెడ్, పార్ట్ ఆఫ్ ఇట్ కెన్ బి అబ్సార్బ్డ్. మీరు వచ్చేసి ఇంకా సమ్మర్ వచ్చినప్పుడు విండోస్ అంతా ఓపెన్ చేసి పెట్టేస్తే రాత్రి పడుకునేటప్పుడు మీ పరుపు హాట్గా ఉంటుంది కదా. Why does the bed get hot? Or even if you leave the window open, your furniture also gets hot. Everything gets hot. Why does it get hot? Because when the radiation is coming there, your bed or clothing or they all absorb the radiation. If they absorb the radiation, obviously temperature will go. That is nothing but absorb. So that is absorption. Whereas if it is a solid body like an iron piece or wood or a bakelite or a paper or a book, it won't transmit anything. Because if you got a book, if I have to see you, if you అర్థం పెడితే నాకేం కనిపించదు. At the same time, if you put a glass in between, I will put the C. That is, there is a transmitter simply. So this is transmitted radiation. This transmitter. The transmittivity, that is called what transmittivity, which is designated by Greek letter of tau. And a part of it will be reflected, which is actually what is called reflected radiation. Reflectivity is designated by Greek letter rho. And this is also same as your density rho, also essentially the same again. So that, I mean, there is no confusion between density rho and radiation rho, simply because radiation ki density ki sambandham ledu. But there are some cases where actually you got convection and radiation, you got distinguished. Then we would rho as rho for radiation, rho for convection, substitute just to make sure that we understand that. So if it is not a transparent medium, there is no transmittivity. So normally if you make the energy balance here, what is coming here, either it has got to be absorbed, or it is transmitted, or it has got to reflect. So the transmittivity plus reflectivity plus absorptivity, both of all of them should be equal to, that is alpha times G lambda plus rho times G lambda plus tau times G lambda should be equal to G lambda. And the G lambda captures is that we get this equation 1 equal to rho plus alpha plus. Obviously, each of these numbers has got to be 1 less than 1 because this is maximum can be only 1. A reflectivity can be 1 when it will be reflected 1. Adamlo chuskunnappudu total figure is reflected. So more or less reflectivity is equal to 1. For mirror, transmittivity equal to 0 because it's all coated. Then absorptivity, because when you are looking at your mirror, it doesn't really get heated up so much. So unless of course you are brilliant, still you can't heat up the mirror. So for most of the solids like steel, wood, cardboard, etc., transmittivity will be equal to 0. For example, if I hold it in front of radiation, this which can't transmit radiation, I can't transmit through it. So we can, by and large, you can say that rho plus alpha should be equal to 1. Alpha is actually what is called absorptivity, and the epsilon is what is called emissivity. Are they related? Are they first cases? Are they coming to nomination? That is what actually Kirchhoff's law will tell you. That we will see next. Okay, is it clear? Let's recapitulating what is emissive power, irradiation, and radiosity. And in addition to that one, this body, because of its own temperature, it may emit some radiation. So this sum of this reflected, what is going out, what is coming in is the radiation, what is going out is simply radiosity. This is basically equal to rho times G and gets on the radiosity. So we got radiosity, we got irradiation, we got emissive power. Is it clear? So these definitions are very important in radiation heat transfer. So then again, there is reflectivity depends upon the surface character. If it is a mirror, what we call as it is called the specular reflection. Sometimes it also gets, for example, your mirror is misted. For example, in the bathroom, you take a shower, okay, and suddenly you can, if you take a hot water shower, there is mist forming on the glass, okay. Then can you see your face in that one? No, you can't. That's because of you have diffuse reflection. So diffuse reflection of no help for us. What we want is specular reflection. That's what. If it is specular, that can be done surfaces. Most of the thermal radiation, we have only diffuse reflection, diffuse radiation. So we don't have to worry about specular. Also, in our radiation lecture, we will not worry about specular reflection at all. So this is what is called a surface. This is called incident ray, reflected radiation by uniform intensity. This is what is called specular reflection. You know, you would have studied in undergraduate, first year physics, angle I is equal to angle R. Okay? That's what is Kirchhoff's law? Now I was telling you what is relation between the emissivity and absorptivity. What Kirchhoff's law says is when the body is in equilibrium with temperature and the equilibrium with the surroundings, the surrounding electron, the total emissive power to alpha is independent of the temperature. That's what is Kirchhoff's law. So the ratio of spectral emissive power and absorptivity, remember, not emissivity. Absorptivity is independent of temperature. That is what is Kirchhoff's law. So from that you can derive that it's independent. It's only a function of temperature. It's not a function of wavelength. It's a function of only temperature. So the absorption at any given temperature, emissivity will be equal to absorptivity. So therefore, But remember, this is only at a given temperature, but independent of the dew. But we have seen earlier that gray body is its emissivity and also is independent of wavelength. Correspondingly, for a gray body, the absorptivity also will be independent of wavelength, but it will only be a function of temperature. Okay, please get this one. It has got to get into our mind. So it is only a function of temperature. It's only a temperature. Later on, you will see in an example how the reflectivity and absorptivity can change with temperature. But it may be at the same wavelength. They are independent. At least what is actually what it comes twice. Okay. Now I don't think I have got time to get through this. Well, I have got 4 minutes. This is essentially basic of when you go out, sun is quite hot. You get solar radiation. So I have given the data of the sun's diameter, distance of Earth from this Earth. This is sun. Radiation is coming here. Approximately the sun's radiation that comes here is about 1368 watts per meter. That is what is called a solar constant. It's about 1368 watts per meter square. ఎట్లా మెజర్ చేస్తారంటే శాటిలైట్లో పంపించి అవుట్ సైడ్ ది అట్మాస్ఫియర్లో అక్కడ మెజర్ చేస్తారు. సో నాసా హ్యాస్ ఇన్ఫాక్ట్ దేర్ ఆర్ సో మెనీ శాటిలైట్స్ దట్ కీప్స్ ఆన్ చేంజింగ్. వాట్ ఈస్ ఇట్ చేంజింగ్? Because the distance from Earth to Sun also keeps changing. Whereas satellites go around the Earth, and Earth's orbit around the Sun is not circular; it's certainly elliptical. Okay? So depending upon the distance, it will keep on changing. So the average is about 1368. From this data, the distance of the diameter of the Sun, diameter of the Earth, distance of the Sun to Earth, and then this you can calculate what the Sun's temperature is. Okay, we'll do it tomorrow. Sorry, sir, I didn't have time to get through this. I wanted to get through this part because I had to spend more time on it.
The problem.
Okay, guys, I will do it tomorrow because in the meantime, I will have this one sent out to you by WhatsApp. Okay, you will get this PowerPoint. One request is that please use whatever we send to you only for your private study purpose. Don't try to sell outside, send it somewhere. It's only for your class, okay? Because the reason is that quite a bit of what I am doing here is actually borrowed from our own lectures from University of West Australia. But usually there is what are called the copyrighted things and other things. I can use for my lectures, there is no problem. I can use it for you people, but you cannot put it in any public domain or anything like that. Please make sure that you don't do that one. That's my request. Because if anyone tests that one, only thing I got to plug it out. That's it. This is most of the the problems and everything is all taken from our lecture notes, what I teach in University of West Australia. Okay, so please. So, what are the rules of the game which I told you in the beginning? Can you please repeat it? What are the rules of the game? No? First rule. Huh? Okay, I will give you 5 minutes to get into the rule, number 1. Second rule, don't wait for me to ask you to come in, you just walk in. Okay? Every time everyone says, please come in, it interrupts my talk. Okay? If you late by beyond 5 minutes, you can come and listen to the lecture, but you don't get the attendance from tomorrow. And in the class, no talking among yourselves, any talking has got to go only to you. Okay? So you can't talk among yourselves. And everyone, when I say use your calculator, you have to sit down paper and pencil, use the calculator to calculate that. The reason is that why I say that these ones are your own good. It's not that I get any lecture or anything out of it. Make you learn. That's what I think. Okay, guys, thanks. Unless you've got any questions, I'm happy to answer any questions. Huh?